Uh, Today we will talk about the other kind of differentiation, which is the divergence of the vector field. So we're still talking about vector calculus. And we're going to talk about the divergence of the vector field. Before we talk about the divergence, we want to introduce the idea of flux. So what is flux? A flux is essentially, remember when we talked about integrating a field over an area? So if I have a field and I integrate it over an area, so I'm kind of trying to find out if this field represents, let's say, velocity of water or velocity of some liquid. This integral of the field f dot ds represents how much of that liquid is flowing through the surface. So that's, for example, an analogy of what flux essentially is. But to define precisely, a flux of a field leaving a closed surface, it doesn't have to be closed, it could be open, but let's look at a closed, volume. So flux in general is just a field integrated. So integrate the field over a surface. That's the flux. The flux of a field leaving a closed volume, if I have a closed volume of space, say this is V, and I want to find out if I have a field F in space. I want to find out how much of that field, let's say that field represents the velocity of a liquid. How much of that liquid is leaving that volume? Is this volume a source or sink of liquid? Then the flux of a field leaving closed volume is defined as just the surface integral, that's it, of A dot ds, but now it's a closed surface. It's a closed surface that's at the border of the volume. So this is a volume, and the surface is at the border of the volume. Right? Now flux plays a role in the definition of the divergence. The idea is that we're going to take this flux and
You're not sharing the screen. Someone just messaged me that you're not sharing the screen.
Okay. I don't know why that happens. Okay, do you see the screen now? Okay. Stupid technology. Okay. Right. So so this is flux. This is the idea of flux. How does flux tie to divergence? Flux is a macro thing. We need to imagine what happens if I do the same calculation, but I do it at a very, very small region of space. Meaning I take the limit as the volume of space goes to almost zero. When I do that, I do like, it's kind of similar to taking the slope between 2 points and then taking the limit at the distance between the 2 points go to zero. Same idea. If I take the flux around the volume and then take the limit of that volume as it goes to zero, that gives me the divergence. So we like to kind of state everything using the fundamental theorem of calculus, right? So restating this in the terms of the fundamental theorem of calculus, the idea is that we're integrating over volume. So we have a volume integral, right? And we're integrating some scalar field. So I have this volume, I have some scalar field U, temperature field, I don't know, charge field, charge density field, mass density field, whatever. Some kind of scalar field over the volume. So the idea, the inspiration that I want to get from integration, I want to define this divergence using integration. So I want to write this integral in terms of its boundary. I want to write the fundamental theorem of calculus for this kind of integral. What's the boundary of a volume? It's a surface, right? It's the surface enclosing that volume, S. So I want to write this in terms of an integral over the boundary. So this is the scalar field, and this is the boundary. And I want to integrate some field f dot ds. And the idea is that I want to obtain u, similar to what we did in the fundamental theorem of calculus. I want to obtain u. I want to relate u to f. So the relation that relates u to f is a divergence. So u is the divergence of f. Right. So this gives me the key to defining what the divergence is. Right. So u is just u and f relate to each other using this. You take f, you operate on it using this operator. And the divergence is essentially some machine that takes in a field f and spits out a scalar field u. So something that takes like a vector field and spits out a scalar field. I don't know. An example could be something that takes in a field of wind velocities and then spits out temperature distribution, something like that. Right? But this is now all you need to define what the divergence has to be. This is all you need to compute the divergence. This is also called the divergence theorem. In many textbooks, divergence theorem, because people sometimes a lot they define the divergence in a different way. So here I'm starting with this as a definition of the divergence. But you could start with something else. You could start with the flux definition and then prove this. Right? But I'm starting with this. I'm starting with saying that I'm looking for some scalar field, nabla.f, that has this property. That if I integrate it over a volume, I get it's equal to the integration over the boundary, because I'm taking my guidance from the fundamental theorem of calculus, essentially. So we want to do this calculation. So how can we do this calculation? Well, u is dot f dv equals s f dot ds. And the idea, as always, when we want to calculate what the divergence is, we want to take the volume to go to 0, or let's say delta v goes to 0. Delta v indicating that this is a really tiny volume of space. So we want to shrink the volume all the way. What does that give us? Gives us, if we shrink the volume so that it approaches 0, that gives us that the term inside the integral becomes constant. Because the term inside the integral becomes constant, I can always take it out. So this becomes divergence f integral v dv. So I'm integrating over the whole volume, but the whole volume in this case is just delta v. It's that tiny volume that I'm shrinking towards. Right? Equals the integral over the boundary of delta v. We can write this way: boundary of delta v. Delta v means the boundary. This means the boundary of the volume. F dot ds. And then I can take delta v to the other side. So I arrive at how I can calculate the divergence. Divergence of f is limit as delta v goes to 0 of the flux around the boundary of that tiny infinitesimal volume, delta v meaning the boundary of that small infinitesimal volume of ds over delta v. And this is just from this property. This is how you would calculate the divergence. This is it. Right. Divergence is essentially what is the divergence? Essentially, the divergence is a measure of how much the field is sourced from a point. Right. That's one way of looking at it. Another way. Okay, come in. Another way of looking at it, trying to get like a physical intuition of what it signifies, is imagine we have a field in space. So this is space, we have a field, blah, 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 an arrow at every point. And then we zoom in to a really small region of space. When we zoom in to a really small region of space, the field becomes uniform. It's similar to when you have a function, the function is wavy, and then you zoom in really to a really small interval, and the function becomes a straight line. So in a similar manner, as we zoom in to a really small region of space, the field lines, the field vectors at every point become more uniform. The field lines, the vectors become more parallel, they become more equal, right? But there is an infinitesimal difference between them. There is, as you move in the space, there is an infinitesimal difference. So let's say like this central, for example, at point P. So around point P, because the region is very small, the vectors are almost equal to F at P, but they vary slightly. Now the question is, how do they vary? And that's what the divergence measures. The divergence is essentially a measurement of the compression or expansion of a field. How does a field, if I have a field, how does the field compress, and how does the field converge, diverge, compress, expand, right? It does not measure how the field twists. For the twisting of the field, like if imagine the field as being like a rope with a bunch of strings tied together, and then you can compress the strings, you can stretch the strings, right? You can bend the strings, but if you twist the string, that's a different kind of deformation, right?
Question.
Yes.
Isn't that dependent on whether the divergence is equal to 0, greater than, or less than 0?
No, it doesn't matter. Well, it tells you what happened. Yeah. Yeah, exactly. So we can imagine. So we said from the definition, we said that we have to look at an infinitesimal volume. Let's say that this infinitesimal volume looks like a cylinder, like this. So having a divergence could mean, and we can imagine, well, let's say F is constant. F is not changing. There's no change in it. F is completely constant. What happens according to this formula?
The divergence would be 0.
Yeah, right. Because F here on the surface of the cylinder is going to be equal to F here. F dot ds is going to be equal. They're going to cancel each other out. F here is going to be parallel to the surface. It's going to all be 0. Right? What would happen? What change? What delta in F? What delta in F is going to give me a divergence? Delta in F is going to give me a divergence as if there is something that's going to cause a flux to come out of this. What could cause a flux to come out of this small infinitesimal cylinder? Let's say that delta F is pointing this way.
Cosine of 90 is 0.
Yeah, something like that. Right? Or delta F, this is delta F, or pointing this way.
In other words, it's oriented normal.
Yeah, let's say like that, oriented normal to the surface. What does that mean? This means that in this region the field is smaller, so the field is smaller here. As I go increase in that direction of F, the field becomes bigger, right? Because you see this is going backwards, so this is subtractive. This is additive, so this is becoming bigger. Bless you. As you move away from the center of the cylinder, you have a vector, and this is delta F, right? So you're shifting the vector. So the vector is being shifted like this, right? So if you have a situation where the field lines are kind of diverging from each other and decreasing in magnitude as you move forward, that's a positive divergence. If you have a situation where the field lines are going close to each other and the field strength is going from small to big, that's a negative divergence. That's a compression. You could have a situation where the fields are completely parallel, but the field strength is increasing as you move forward. that's still a sort of compression. It's a linear compression. So in essence, the physical way of trying to understand divergence, rather, if you're not satisfied with the purely mathematical equations, is if you imagine the field to be some sort of fluid, and the divergence is really measuring the compression of that fluid. If the fluid diverges, that reduces the compression. If the field converges, that makes everything more compressed. If the field does this linear sort of compression thing, right? So this is what divergence is measuring. However, divergence is not measuring the twisting of the field. Let's say you have a bunch of strings and you twist them like this. That's not divergence. That's going to be measured by the thing that we're going to study next, which is the curl. Yes, exactly. How do we calculate the divergence? So calculating divergence. Again, as I said in previous lectures, that will depend on your coordinate system. So what coordinate system you choose is going to tell you what the divergence is. So simplest is to start with the Cartesian system. So for the Cartesian system, we need to consider that the infinitesimal volume is going to be something like this, like a cube, right? And then dot, 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 dot. Let me see if I can draw it better. Let me draw the cube bigger. I don't have to draw it. Although it's infinitesimal, I do not have to draw it really tiny. So the distance, so this point here is let's say x. This point here is at x plus delta x. This point here is also, this point here is x, actually y, z, right? So this point is at x delta x. This point is at z plus delta z. This point is at y plus delta y. X plus delta x, of course, y, z, y, x, x. Okay? So those are the boundaries of the cube. Of course, this point here, we don't need this point, but this is going to be x plus delta x, y plus delta y, z plus delta z. And our field is the following. Our field is f equals fx, x hat, plus fy, y hat, plus fz, z hat. And from the definition, divergence of f is the limit as delta x, delta y, delta z go to 0 of what? Of the flux coming out of the surface. Let's see. So this is the surface, and then we want to measure, we need to kind of determine the normals. So the normal to each face here. So this is the normal. And then I can write it down as what? As what's the flux along this surface? Only fx is pointing out of this surface, right? Fy and fz. Yeah, this leads essentially to Gauss. Well, we want to just calculate the divergence at this point. We're not there yet. So what do I want to say? F has a component. So for this surface, the y and z components don't matter, right? Because the y and z components are 90 degrees with respect to this normal. So integrating over this surface here is going to be fx, x plus delta x, y, z. This is the value of the field times the surface area, which is what? Which is delta y and delta z. It's going to be delta y, delta z. Minus now the back plane. The back plane is going to be in the opposite direction, and it's going to be, because it's going to be inverse to the normal to that surface. Remember, the normals always point outwards. So it's going to be, has a negative sign, fx xy z times delta y delta z. The whole thing is divided by well, we're not done yet, actually. We're not done yet. We have now to do, we did 2 surfaces. The cube has 6 surfaces. So we have 4 more terms to do. So we have to add fy. Now let's do this surface. So this is going to be fy x at y plus delta y z. This is what? This is delta x. This is delta z. So it's going to be delta x delta z minus fy xy z delta x delta z. And then finally, yeah, this is the other surface, the minus the other side. And now we do the top and bottom surfaces. So that's going to be plus fz. And again, top and bottom, only the z component counts. It's going to be fz x y z plus delta z delta x delta y. Again, because the sides here are delta y and the side here is delta x, minus fz xy z delta x delta y. The whole thing, this whole thing, is divided by the volume element, which is delta x delta y delta z. So if I cancel, so the 2 terms, if I cancel here, I cancel, let me assume that I cancel everything. So I cancel here delta y delta z, and delta y delta z, and what remains is delta x. I cancel here delta x delta z, and what remains is delta y. And cancel here delta x delta y, what remains is delta z. So you see what's taking shape here? What's taking shape is this is the differentiation of the fx component with respect to x. This is the differentiation of the fy component with respect to y. So in Cartesian coordinates, really the way to calculate the divergence is as follows. You take the x derivative of the x component, the y derivative of the y component, and the z derivative of the z component. So this is how you practically compute the divergence at every point in space. If someone gives you a vector field, this is how you compute the divergence at every point of space. This is only true for cylindrical, Cartesian coordinates, excuse me. For a cylindrical system, you have to do the transformations. You have to transform both the operators. So for a cylindrical system, what we have to do is we have to transform the operators, right? So we have to write delta over delta x as a function of delta over delta r, delta over delta v, delta over delta z, so on and so forth. And then we have to transform both all 3 operators, and then we have to transform fx, fy, fz. So the way you would go about doing it, and everyone needs to do this once in their life, is, for example, the delta over delta x operator. How do you transform it into the Cartesian, into the cylindrical system? Well, it's going to look something like this. It's going to be cosine phi delta r. This is all from the chain rule. Sine phi over r, delta over delta phi. So this whole thing is delta over delta x. And then I need to transform fx. Fx into cylindrical coordinates is just fr, cosine phi minus f phi, sine phi. This whole thing is our old fx. And then you simplify, you do with this calculation. Of course, this is not done yet, so I have to add also cosine phi delta over delta r minus cosine phi over r delta over delta. It's a hairy calculation, but it's doable. The only difficult thing about this is that it's cumbersome. Other than that, it's just a matter of transforming both the components and the operators. Right? Plus finally, the z part is simple. It's the same, delta f z over z. So this is our old delta over delta x, and this is our old fy. And if you do the simplification and everything, it turns out that the divergence formula, the divergence itself is going to be the same at every point in space, regardless of the coordinate system. Because space is not aware of any coordinate system we impose on it. It's a human invention, right? But the calculation is going to be, the way we arrive at the same solution is going to be, the number is going to be different. So in cylindrical coordinates, it's going to be 1 over r delta r fr over delta r plus 1 over r delta f phi over delta phi plus delta fz over delta z. If you have any divergence field, any field, it's a given that this at every point in space should always be equal to this. If you have a certain point in space and you do the calculation in Cartesian coordinates and you get a number for the divergence, and then you do it in cylindrical coordinates and you get a different number, something is very wrong in your calculation. Because the divergence itself is a physical quantity. It doesn't care about what the coordinate system choice is. We can do something similar for the spherical system, and I leave going through this calculation as an exercise. Again, everyone needs to do this once in their lives and then forget about it and just look up tables or appendixes in the back of textbooks. But the divergence in spherical coordinates, when you do it, when you start with Cartesian system and you transform all the operators and you transform all the components and you carry all the algebra out, it's going to turn out to be something like this: 1 over r squared delta over delta r capital r square fr plus 1 over r sine theta delta over delta theta f theta sine theta plus 1 over r sine theta delta f phi over delta phi. Okay. You mentioned Gauss's law. Gauss's law, although we're not there yet, but Gauss's law really has everything to do with the divergence theorem. So here we're treating everything mathematically, right? So we don't know about charges and fields yet, electrical fields. But essentially, this is what Gauss's law is, this divergence theorem, or this fundamental way of stating or defining the divergence, which is through something that's analogous to the fundamental theorem of calculus. In more advanced studies, they would call it Stokes' theorem or generalized Stokes' theorem, right? But in the physical interpretation of this, the scalar field will be something like the charge density in space. That is the scalar field we're concerned with. And the field that we're integrating on the boundary is the electrical field. So what Gauss's law, this is exactly Gauss's law if you add physics to it. If you consider F to be the electrical field and you consider U to be just the charge density, this tells you that if you integrate the electric field over any closed surface, no matter what it is, it will always be equal to the total charge enclosed in that surface. Right? But we don't know anything about electrical fields and charges at this point. We're only treating this mathematically at this point.
What about electric flux?
This is electric flux. Yeah. So before I go into circulation now or curl, I want to let's do quick examples from the textbook. Simple examples, really. This is all mechanical once you know what the formulas are. So let's say someone tells you, your grandma comes and say, hey, suppose there's a field that's equal to 3y x hat plus 5 minus 2x y hat plus z squared minus 2 z hat. What is the divergence of that field?
5 minus 2x.
So you have to take fx and differentiate with respect to x, right? It's going to be 0. You have to take this and differentiate this with respect to y. It's going to be 0 too. There is no y. However, you take this and differentiate with respect to z, it's going to be 2z. So this is the divergence. The divergence of this sort of field only depends on your z coordinates, right? Let's do an example in spherical coordinates. Let's say someone gives you the field in spherical coordinates. So let's say someone tells you A equals 0.2 r cubed phi sine squared theta r hat plus 0.2 r cubed phi sine squared theta phi hat plus 0.2 r cubed phi sine squared theta phi hat. What's the divergence of this thing? Well, the divergence, we have to go back to the formula. After you've done this once in a lifetime derivation by hand, you would commit it to your notes, or it's going to be in some table in the back of a textbook. You'll go here and say, hey, this is the definition of the divergence in the spherical system. So you just apply it. So this is going to be 1 over r squared. And then you have to take fr multiplied by r squared and then differentiate with respect to r. So if I take fr, which is this, ar, and multiply it by r squared, I get r to the power 5. And then differentiated with respect to r is going to be 5 r to the power 4. 5 times 0.2 is 1. So it's going to be r to the power 4 phi sine squared theta. Okay. So this cancels. This becomes r squared. And then I'm going to do now the second term. The second term, 1 over r sine theta. So I need to take f theta, or a theta in this case, which is this. This is a theta. I need to multiply it by sine theta, so I end up with having sine cubed here, and then differentiate with respect to theta. So this is going to be 0.6 for the sine cubed, r cubed phi sine squared theta, right? I'm differentiating the sine cubed, and then I differentiate the sine, which becomes cosine theta, right? And then this whole thing is divided by said r sine theta. So r cancels this r, this becomes 2, r squared. Sine theta cancels this squared, becomes sine theta cosine theta. And then I'll do the final term. There is a 1r sine theta here, delta f phi over delta phi. So this is delta f phi over delta phi. Phi is just a constant. So this becomes simple. This becomes 0.2 r cubed sine squared theta divided by r sine theta. R cancels this r squared. Sine theta cancels the sine squared. We end up with only sine. So the divergence becomes r squared phi sine squared theta plus 0.6 r squared sine theta cosine theta plus 0.2 r squared sine theta. That's the divergence at every point. And if someone gives you a specific point in space, let's say someone tells you at 2, 30 degrees, 90 degrees, you can plug everything in, Ln, and find the divergence. In this case, the divergence of A is going to be 3.603. So I want to talk now. So this is kind of like the second kind of differentiation we introduced. We could have introduced this first. Why do I say we could have introduced this first? Because this has a nice property that we're tying something. So we're integrating over a volume, and we're tying that integral in the volume over the boundary. There is no ambiguity on what the integral over the volume is, because the volume, we know there are no two options. Remember when we were integrating between two lines, the boundary, remember when the boundary is two lines, we had a choice of integrating over this line, this line, this line. So we have to state, we are interested in integrals over lines such that the result only depends on the endpoints. So not all kinds of fields are possible in this case. The only fields that the divergent, what's called the gradient fields, are the fields that result. The gradient fields are the fields that can be obtained from a gradient, meaning they are the sort of fields that are conservative, meaning that when you integrate them from point A to point B, from the fundamental theorem of calculus, you know that if you integrate the line integral from point 1 to point 2 of a gradient field, something that is generated from a gradient, dot dl, that's going to depend on the endpoints, u p2 minus u p1. Right? So such a field will naturally be a conservative field because the integral is going to always depend only on the endpoints. So there is kind of like a basic property imposed by having a gradient, which is that it doesn't matter what path you integrate. In the volume case, it doesn't matter, because if you consider a volume and the boundary of that volume is a surface, it doesn't matter because there is no ambiguity. The volume, there are no 2 or 3 ways to integrate a volume bounded by a surface. There's only one way to integrate a volume bounded by a surface, which is to integrate over that volume. So it would have been perhaps more natural to introduce the divergence first. But that's fine. We start with the gradient because typically that's how textbooks go. The next thing now, if we had started with divergence first, the next progression would have been, okay, what happens if I integrate over a surface? What is the boundary of the surface? A boundary of any surface is a closed curve. So this is a closed curve, C. This could be a boundary of any surface. This could be the boundary. Imagine like a child, you know those bubble toys where you bubble soap, where you blow on the bubbles. So imagine this ring here is like the hoop of the thing that you plug into the soap, and then you blow on it. So this could be one surface. This could be a second surface. This could be a third surface. Right, this is S1, S2, S3. And I mean, what I want you to imagine here is that this hoop, this red hoop, is like the hoop that you plunge into the soapy water, and then the surface is like the bubble that starts to form once you blow into the hoop. Right? So we are now interested in representing the integration across the surface, S1 or S2 and S3, in terms of the boundary. So you want to utilize the fundamental theorem of calculus here. But having said so, that implies, having decided to do so, that implies that this is a sort of integral where it doesn't matter what the surface is if they share the same boundary. So the integration over S1 and S2 and S3 should give us always the same value because they all share the boundary. Not for every possible field, for some fields. And those fields where this is true are called divergence fields. Right? And this is very useful in electrostatics, is that it doesn't matter what the surface around the charge is, you'll always get the same. The flux will always be the same. It's like you have, even water, if you have water sprouting out of the nozzle, it doesn't matter what surface you have so that around that nozzle, so that you measure the speed of volume of water going out, it will always be the same. Whether it's a circular surface or a cylindrical surface, it will somehow all end up being the same, because the physical thing that's happening, the water pouring out, does not care about what surface you imagine, right? So, and this is now the key to introducing the curl. The idea of the curl is that we want to represent a surface integral of some field, let's call it f dot ds, by an integration over the boundary. Again, that idea from fundamental theorem of calculus. Represent an integration over an interval by integration over its boundary. What is the boundary in this case? The boundary is that ring around the surface. So I have the surface, let's say, and the boundary is this red thing here. This is the boundary. I don't know, it's a terrible drawing. Something like a balloon, let's say. Like a balloon, a soap bubble that's almost gonna, float, leave the, right? And this is the boundary, the blue curve here. So surface integral, I relate it to a line integral. So this is gonna be, and this is a closed boundary, because the boundary is always gonna be closed, right? So it's gonna be closed boundary of over L, some other field, let's call it A dot DL. Okay, and now we said the other trick. Now I want to relate. I wanna have A and F relate to each other. So I want to be able to get F from A by some kind of operator, and that operator is the differential operator. And in this case, that differential operator is the curl. Something else, because we're getting it in a different way. When we were dealing with volumes and surfaces, we got the divergence. When we're dealing with surfaces and line integrals on the boundary, we get the curl. When we're dealing with line integrals and the boundaries being 2 points at the end, we get the divergence. We get the gradient. So in this case, this is going to be the curl of A. Right? And this is it. This is the definition of the curl. This entity here is what's called the curl. Okay, I think I'll continue this next time. Oh, no, we have 5 minutes. I'm confused. I thought we started at 9. Okay. All right. So we have 5 minutes. So yeah, this is the curl. And this is enough to calculate what the curl is. And the trick again, the trick here, as we said, is to make the surface become infinitesimally small. Same way we made the volume infinitesimally small for the divergence, we make here the surface infinitesimally small. For the gradient, we made the distance between the 2 points infinitesimally small, the line and the curve infinitesimally small. So if we make the surface infinitesimally small, we can take this out of the integral, and we can now really define what the curl is. So if I'm able to take this if delta S. So this is, let's say, if the surface is really tiny, delta S, really infinitesimal. So delta S goes to 0. I can take this out of the integral, so I end up with curl A S ds. Well, this is a little bit. Remember, ds is a vector. So if you take an infinitesimal area, remember we said that areas, when we go infinitesimal, they sort of become like a vector. They have a direction, they have an orientation. So it's not enough to say that the area is infinitesimal. We have to specify, okay, infinitesimal in what direction. For a volume, it doesn't matter. We can make a volume really small. It becomes symmetrical any way you look at it. For an area, when you make it infinitesimal, You have to ask yourself, okay, where is it pointing? The area, the disk of the area, where is it pointing? What direction is it pointing at, right? And we want to encode that thing by writing cross A dot the direction of S, representing it by a unit vector in the direction of the infinitesimal area. So this is a certain direction, normal to the area. Actually, I can write dot n hat. So this is like a normal vector to that infinitesimal area with magnitude 1, and this multiplies by delta S. I just wrote ds in terms of this, essentially. Delta S. I can, sorry, magnitude of ds. What I can do now, I can remember this is a sum. So this, because the area is really small, this is constant. So I can use the linearity of the dot product by taking this out. It's like if you have, we said A dot B plus A dot C plus A dot D. A is constant, you can take it out. This becomes A dot B plus C plus D. So in the same manner, here we have a sum of dot products where A, nabla cross A is constant. We can take it out as a common term. So this becomes curl A dot n hat is constant. Integral of ds over the whole area is just delta S. So this becomes dot n hat delta S. The whole thing is multiplied by delta S. Yes, which now I can take to the other side. So this becomes A dot dl. Yeah, this is sometimes called, yeah, this is called Stokes theorem.
So is Green's theorem used much in this class, or is it mainly?
It's the same. Green theorem, Stokes. See,
On most of the surfaces, we deal with 3-dimensional or 2-dimensional.
3-dimensional. We're talking about electromagnets.
Imagine we probably would use Stokes theorem a lot more than Green's.
See, Green's theorem,
I know they're the same, but
they're the same thing.
I know that, but like we still would probably use. Or
We use both. We use Stokes and Gauss's theorem the most. Yeah. But they're essentially the same thing. There's something called a generalized Stokes theorem. Yeah. So if you take limit delta S goes to 0, this is really the physical. This gives you an idea what the curl is. I'm going to talk a bit next time about the physical intuition of what the curl is. So we start with the mathematics. We're going to talk a bit about the physics, but in short, the curl is about, if the divergence was about how the field is compressed and expanded, right, how it diverges and converges, the curl is more about how the lines of force of the field twist and shear. So it's kind of like a different sort of differential change in the field. It's interesting that when you go to higher dimensions, things can change in different ways, infinitesimally, rather than just one way. So I'm gonna stop here.